we saw that increasing the complexity and nonlinearity of the model was very helpful to fit to our nonlinear data, to our complex data. But then there's a side effect that comes with that increasing complexity. We start to see overfitting, unfortunately. I'll make a demonstration here of how overfitting looks like. Fortunately, with our model with 16 neurons and 4 layers, we didn't see too much overfitting. Well, our data didn't have much noise, but we'll definitely see that in larger data sets. Let's say we have a model that has a width of 512 neurons and a depth of 128 layers. When we have this type of complexity, you can look at the number of parameters here per layer. The number of parameters, it just skyrockets. It's insane. We end up having hundreds of thousands or even millions of parameters when we start to increase the complexity of models too much. And this very, very large networks, they could be good to model very complex data that has millions of features, but it could generate another side effect of just overfitting, just fitting to the noise of the data rather than really learning some pattern in the data. And in the theoretical session, I talked more about what are the causes of overfitting, why it happens, how it looks like, but I just wanted to make a short demonstration here. So let's create our data set first. So I boosted the amount of noise a little bit to make it more noisy and to make it more complex. So we will have more chances of overfitting. So a typical data set that could generate overfitting is a data set that is very small and has a lot of noise. Then we apply a complex model on top of that. It's perfect chance for overfitting. We have our candidate here. Let's first go ahead and build our linear model that we have implemented before, a linear neural network without any nonlinear activation, very simple. And let's see how it looks like. So we're basically gonna be fitting a linear model, not bad, a loss of less than 0.1. It's okay, it has some slope there in the end with the outliers here, but it's still fitting pretty fine. So you can see the blue dots are original simulated data, and the orange line here is our model fit, predicted values of our fit model. So if you want to see the trainable parameters in your model, you're basically going to see a tensor like that describing the number or the ID, which is an arbitrary number for your layer, the kernel ID as well. And you're going to see, for example, the value of your weights and the value of your biases. So you can see this kind of tensor structure data here, a lot of specifications and values to those specifications. And what type of data it is a floating point number with the precision of 32 bits, for example. So you can see all the descriptions in the tensor. All right, so we see that as a very simple model fits to that pretty well. What if we created a more complex model? Maybe would we observe overfitting or not? So let's create a model that is overkill for this data with nonlinear activations, with many layers and many hidden units or neurons. When you open this notebook, you are not going to see this chunk of code because I made this as an exercise for you to answer one of the quiz questions. So I'll ask you to implement this and tell me what are the numbers of parameters that you see and what are the loss values that you see. So I have the instructions here for you to build your model with 4 hidden layers and make all layers of your neural network except the output layer to have ReLU activations, the rectified linear unit activations, and set a width for all layers except the output layer of 64 neurons. So after you implement that, you can run the training of your model, same process as before, generate the data, split into batches, build your model. Here I'm building first the linear model again, just to have a baseline for comparison. And then I'm building the nonlinear model here. and summarizing, compiling, and fitting. So after that, we're gonna plot. We're gonna plot our original data. We're gonna plot the linear fit for comparison, and we're gonna plot our nonlinear fit. So let's see. So you see that the orange line, or linear fit, it shows a very linear fit to the data. It's less overfit to the noise. And then our nonlinear complex fit, it starts to wobble around the green data points here. It starts to wobble around. It starts to fit to the noise, to those points that deviate a lot from this linear distribution here. That's when we start to see overfitting. But we actually increase here the complexity of the model a lot, and that's why we are observing overfitting. Sometimes it's more difficult to detect overfitting. Sometimes the overfitting doesn't show in the training data. It will really show when you partition your data in a portion that you're going to use for training your model and another portion that you're going to use to evaluate your model, because the model will start to fit to the noise in your data, and it will have a terrible accuracy when you provide a new portion of data that the model has never seen, because it will not know what to do to that new noise that it's observing. It's not really fitting to the trend in the data. It's just fitting to the noise of the training portion of the data set. So it will do terrible in the new portion of the data that has never been fit to.